3.8.3 Damping. Now that we've covered free and forced oscillations, the next key phenomenological effect is damping friction, and this finally gives us a first-order time derivative term in the equations of motion, e.g., we now have an opposing frictional force linear in velocity F equals minus alpha x. See the next equation. To solve, try the form x equals exp of Rt, which has roots of characteristic equation. R sub 1 2 equals minus lambda plus or minus the square root of lambda squared minus omega squared. Thus, x of t equals c sub 1 the exp of R sub 1 ton, plus c sub 2 ex of p of R sub 2t, in the general solution, and we have the following cases. Case is less than omega, exponentially damped oscillations. See the equation shown. Notice that there is a decrease in frequency since friction retards motion.
Case equals omega, exponentially damped with no oscillation. See the next equation. Case is greater than omega, aperiodic damping. See the equation shown. 3.8.4 First encounter with the dissipative function. Consider friction in the multidimensional case with north greater than 1 degrees of freedom F sub I equals minus the sum from k2 of alpha sub I kx sub k. To avoid rotational instability or other statistical mechanics pathologies, we require alpha sub I k to be symmetric, thus we can introduce a dissipation function script f. See equation 3-55. Let's consider the rate of dissipation of energy in the system.
See equation 3-56. Thus script f is proportional to the rate of dissipation of energy as its name suggests. 2.8.5 Forced oscillations under friction. In this section we combine both the frictional force and driving force in combination. The general form of the differential equation describing forced oscillation with damping complex form is, see equation 3-57. Try x of t equals b the exp of I gamma t for the particular solution, then the characteristic equation gives us, see equation 3-58, where
see equation 3-59. Adding the particular solution to the general solution for the homogeneous equation, and taking omega is greater than lambda for definiteness in what follows, and taking the real part as our solution, we have, see equation 3-60. And after sufficient time, there is just x of t approximately equals b the cosine of gamma t plus delta. Near resonance, gamma equals omega plus epsilon. Suppose also that lambda is much less than omega, then see equation 3-61.
The phase difference delta between the oscillation and the external force is always negative. Far from resonance, gamma is less than omega delta vector 0 and gamma is greater than omega delta vector minus pi, while passing through resonance gamma equals omega delta vector minus 1/2 pi. In the absence of friction, the phase of the forced oscillation changes discontinuously by pi at gamma equals omega. When friction added, the discontinuity smooths out. Once steady-state motion is achieved, x of t approximately equals b the cosine of gamma t plus delta. Energy absorbed from the external force matches that dissipated in friction. We have the rate of dissipation due to friction previously as minus 2 script f, where script f script equals 1/2 alpha x squared equals lambda mb squared gamma squared the sine squared of gamma t plus delta. With time average, 2 script f bar equals lambda mb squared gamma squared. Thus the energy absorbed per unit time is lambda mb squared gamma squared. Now if we want the integral of the energy absorbed at all driving frequencies, the absorption will be dominated by the frequencies near resonance, for which the integral approximates as pi f squared of /4m.
Note, in this analysis we are considering the spring or pendulum with only a linear restoring force. For the pendulum in the small angle approximation, however, such is the case, where the force due to gravity term is minus mg of sin of theta approximately equals minus mg of theta. When we return to the damp-driven oscillator without this approximation later, we will see that chaotic motion becomes ubiquitous among the possible motions elicited. Before moving on from the topic of dissipation, and to get a glimpse of the phase diagram representation used in the Hamiltonian approach to be discussed next, let's consider the system. See equation 3-62. When the potential is a double well. In figure 3.12 is shown a sketch of the potential of the system phase diagram when gamma equals 0, no dissipation, and of the system phase diagram when gamma is not equal to 0. For the system with dissipation, we see that there is a decaying spiral that selects a well to localize to when the energy dissipates to the level of the separatrix. Figure 3.12. Left, a sketch of a double well potential. Middle, sketch of phase diagram with no dissipation, phase diagram with dissipation, and eventual settling into the right well.
2.8.6 Parametric resonance. Instead of an external force, let's now consider modulations of the system parameters themselves. System isn't closed. For an external force driving the system at resonance, we found linear growth over time in system displacement from equilibrium. For parametric resonance, we will see this growth at resonance is exponential, where the growth is multiplicative, but this also means this resonance growth phenomenon doesn't occur if the displacement or system is at equilibrium to start, because multiplying the growth times 0. An example to keep in mind is the familiar swing. Once set in motion, with non-zero start, the swing motion is sustained by the appropriate resonance matching timing of swing motion with swing cycle, a parametric resonance. To capture the phenomenon, let's consider a 1D spring system with mass and spring constant K. See equation 3-63. Let's rescale time to allow the presumed time-dependent m, t, to be separated. See the next equation.
Thus, without loss of generality, log, we can consider the problem in the form. See equation 3-64. That we could have arrived at from the start, allowing m equals constant, but arriving at a form with a time-dependent system frequency omega of t. Consider the case where omega of t is periodic with frequency gamma and period t equals 2 pi divided by gamma. If omega of t equals omega of t plus t, then the overall solution is invariant to t vector t plus t. In turn, this means that the two independent solutions for displacements, x sub 1 of t and x sub 2 of t, must also be invariant to t vector t plus t, as can be seen by substitution in the above second-order differential equation, aside from a non-time-dependent constant factor, thus the general solutions must satisfy. See the equation shown. The most general solution is then.
See equation 3-65, where p sub 1 of tt and p sub 2 of tt are purely periodic functions with period t. It turns out, however, that the constants c sub 1 and c sub 2 that are exponentiated in the solutions have a relationship that forces one of them to always be the inverse of the other. Thus, there will always be an exponential growth term. Consider. See the next equation.
If x sub 1 x sub 2 minus x sub 1 x sub 2 equals constant, then with t vector t plus t the extra overall factor of c sub 1 c sub 2 that results must equal 1, i.e., 1c is the inverse of the other. This is referred to as parametric resonance, but observe that it happens for any parametric driving frequency. Practically speaking, the accessible domain for this type of resonance is more restricted, as the derivation that follows relates. Note, the boundary conditions might be such that the purely periodic functions are simply zero, a special case where exponential growth doesn't occur because it's zero to begin with. Since parametric resonance is a generic phenomenon when modulating a system parameter, is there an optimal frequency to do this? The answer is yes, and it's simply double the system's natural resonant frequency. In real-world applications with drag, this optimized driving frequency can often still operate at parametric, exponential growth, resonance. To show the specialized resonance in the drag-free case, start with the frequency parameter split into the time-independent resonant term omega sub 0 squared and time-dependent offset multiplier term. See equation 3-66.
Where h is much less than 1, and we choose gamma equals 2 omega sub 0 plus epsilon, where epsilon is much less than omega sub 0. Let's try a solution of the form without parametric modulation, then account for that modulation by an offset to the natural frequency that matches with the parametric driver frequency. See the equation shown. Substituting the above solution and expanding to first order in h and first order in epsilon, where a, t and b t very slowly compared to omega sub 0, and assume a tilde epsilon a and b tilde epsilon b, later verified in result. First consider the trigonometric cross terms. See the next equation. Note the higher multiple frequency in the first term that results. Higher multiple frequency terms will contribute a higher order of smallness with respect to h, thus like higher order h may be dropped in the first order analysis. The resulting equation is.
See the equation shown. The coefficients of the trig terms must independently be 0. Let's try of t tilde exp of st and b of t tilde exp of st, which gives rise to the characteristic equations. See the next equation. Note that the solution range for exponential growth is where s is real, thus we have the constraint. See the equation shown.